Welcome to day 49, L'Hôpital's rule. We'll talk a little bit more about this name. You might notice here it looks like L'Hôpital and it has this very cool little accent, circumflex over the O. And then sometimes you'll notice that I spell it like La Hospital. La Hospital. And as one student so wonderfully asked, did he invent hospitals? And I'm fairly certain she was kidding. However, no, sadly, he did not invent hospitals. So we will discuss this French gentleman later on. For now, we're going to start with a nice review from last class. If you might remember, last class was on the mean, the Rood value theorem. No, just the mean value theorem. And it's not quite the average value theorem. That's going to tell us something else. The mean value theorem just reminds us that if you find the slope of the endpoints, or better said, the slope of the secant line, that there's some value between a and b where if you take the derivative, that derivative will be equal to the slope of the secant. That's our mean value theorem. And of course, this is also known as the average rate of change, so mean value theorem might make a little more sense. Your opener today, though, is all about theorems. Explain why, explain why. Let's see what you can do with it. There's a nice table over to the right, and then we will discuss from there. Ready, set, go. All right, let's see how we did here. We've seen this problem several times so far this semester, but it's okay if you don't remember it, because part B we have never seen before. Part A, explain why there must be a value blah, 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 such that h of r equals this. I'm not seeing any sort of derivative here, or limit here. It's a theorem. This theorem is asking to guarantee a value. So I'm thinking probably the intermediate value theorem. I think we'll probably need to find h of 3, and we'll also need to find h of 1. H of 3, we have a formula up here. We have f of g of 3 minus 6. So g of 3 is 4. F of 4 is negative 1. Negative 1 minus 6 is negative 7. Very exciting. And then we also have h of 1. H of 1 is going to be f of g of 1 minus 6. G of 1 is 2. And f of 2 is 9, so 9 minus 6, I'm getting 3. Cool. So we found the point h of 3, which is negative 7, and h of 1, which is 3. And you'll notice that negative 5 is also an output. They said we plugged something into h, and we got negative 5 as an output. Negative 5 is between negative 7 and 3. This is definitely an IVT question. So don't forget, we'd say something like f of x is continuous. Ooh, but wait. They didn't tell us that anything was continuous up here. We need to be a little more specific here. They did tell us that f and g are differentiable. But what does that do? Well, differentiability implies continuity. If something has a slope, then it has to have a continuous point there. But we do actually on the AP exam need to state that. It doesn't even need to be in the problem. It can be up above. It can be something like as f and g are differentiable, then they are also continuous. And the AP exam last year in the end of 2019 to 2020 was incredibly specific on this. If a student did not put a sentence like this, it was an IVT question, and they just launched into as f is continuous, then they lost a point. They were very, very picky. So be careful about that. If you state a fact about continuity, then it better have been told to you in the problem, or it needs to be obvious. And differentiability being continuity is not considered obvious. You do need to state it. All right. Now, this last part, though, you might say, well, wait. Then do I have to say that because f of g of x is a composition of continuous functions and 6 is also continuous, that h is continuous? No, you don't. They take that as self-evident, strangely. So we do something like this. As h of x is continuous, and we're going to show that this value is between these values. I don't like holding negative 7 and 3 kind of on their own. I much prefer those inputs like so. H of 3 is the smallest, then negative 5, then h of 1, then the IVT does all of this stuff. It explains why there must be a value, blah, 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 blah. Cool. Part B. Explain why there must be a value c such that 1 is less than c less than 3 such that h prime of c equals negative 5. Well, there's actually two ways to potentially do this problem, and I'll show you the wrong way first. And this is a very tricky problem because you see h prime, you're like, we just did the IVT. Should we do the IVT again? Well, first, it is certainly possible to try and use the IVT. It ends up not working here, but it's not a bad way to go. However, the reason I would hesitate to use the IVT is because you already used it once. And the AP exam, even though it's like 4 hours long, they seldom repeat themselves on free responses. So if you use the mean value theorem somewhere, you probably won't use it again. Of course, watch this be the year where you use it like 2 or 3 times. And the reasoning is because on the free response, they try to assess as much calculus knowledge as they can, and they don't have enough time to repeat questions. So I'm guessing it's probably not the IVT, but I'll show you why, and then I'm going to erase this because I'm going to run out of room. So here's how we would do the IVT. We would take this function, and we'd find the derivative first. Right, and the derivative I'm just going to state up here again in the interest of space because I won't need it again either. H prime of x, we have our chain rule. Derivative of the outside, inside stays the same, times the derivative of the inside. Minus 6 becomes minus 0, so who cares? All right, then we'd probably try to go the same way as before. So we'd find h prime of 3, that's f prime of g of 3 times g prime of 3. And we'd simplify this down. Again, don't take too much out of this because I'm going to erase it. G of 3 is 4. I like to do both the derivatives at the same time. I don't know why. So f prime of 4 is 3, and g prime of 3 is 2. So we get 3 times 2, which equals 6. All right, looks good so far. And then, of course, we also have h prime of 1. So f prime of g of 1 times g prime of 1. F prime of, what is g of 1? Jumping back over here. Looks like g of 1 is 2. Yeah, so we get f prime of 2, which is 2, and g prime of 1, which is 5. So we get 2 times 5, which is 10. Now, you might say, well, 6 and 10, those are the endpoints. Negative 5 is not between those, so there doesn't have to be a value. Well, first, this is an AP problem. They're not going to lie to you. It says explain why there must be a value. There has to be a value. So if you're saying like, ooh, I did all the math right, negative 5 is not there, I caught those AP writers. No, you didn't. They're not wrong. Unfortunately, the AP exam goes through a million different people to read, write. They test problems in previous years. They know what they're doing. There is not a mistake here. That's on you. Well, what you're doing is you're kind of making a false conclusion, because although the IVT tells us that if the value is between the endpoints, then it must exist, it does not say if the value is not between the endpoints, then it doesn't exist. And I'll draw you a cute little picture. Here's 1, here's 3, we had 1 comma 6, and here's 10. So we had 1 comma 10 and 3 comma 6. And negative 5 is way down here, just hanging out. So you could say, well, duh, if you connect these two, clearly negative 5 is not between. And then we'd say, well, wait, why is it linear? Couldn't the graph go like this? And it certainly could, because all the IVT guarantees is that every value from negative 6 to 10, so this part, must occur, or from 6 to 10. So that all has to happen. It is not guaranteed that there won't be more that happens. So either way, though, the IVT does not work here. And since I mentioned that this directly connected to yesterday, we should probably be thinking the MVT, because the MVT is a really nice way to guarantee a slope. How does it guarantee a slope? Well, the first thing that has to happen is that h has to be differentiable. Well, similar as to before, even though we didn't state it, since f and g are differentiable, compositions of differentiable functions will generate a differentiable result. And to start with the MVT, we always want to find the slope of the secant line, the slope of the endpoints. And that's found by doing h of 3 minus h of 1 divided by 3 minus 1. H of 3, oh, we did that up above. So this is actually really clever, and they do this a lot too. You're like, oh my gosh, I have to plug more numbers in. No, it's the same numbers. So the first one is negative 7. The second one is 3 divided by 3 minus 1. So I'm looking at negative 10 over 2, which is negative 5. Is it a coincidence that they matched? No. No, it is not. What this is telling you is that the slope of the secant line of the graph of h, the original graph, if I were to graph whatever this is, and then you were to connect the two endpoints, that slope is -5. Guess if it's negative, it should be going down, huh? -5. Cool. What does the mean value theorem guarantee? The mean value theorem says, cool, you connected those guys together. Well, it was pretty terrible. You connected those guys together, the slope of the secant. There's going to be some value, I should have done it like this, there's going to be some value between those points where you can draw a parallel tangent line, that there is a slope of a tangent that is the same as the slope of the secant. How do we conclude here? As h of x is continuous on, right, 1 to 3, and h of x is differentiable on 1 to 3. I should just use parentheses here, probably easier. Right, that's our preamble for our MVT every time. Then what happens? Then, as h of 3 minus h of 1 over 3 minus 1 equals -5, the MVT, and then this is where I get very lazy. The MVT, let's put little asterisks here, put an S, explains why there must be a value c for 1 less than c less than 3 such that h prime of c equals -5. Great. That's that. So using that MVT definitely comes up. It'll come up once a year on the AP exam, almost always does. Be ready for it. It is the 4th of our 5 total theorems. However, that has nothing to do with today, so let's go ahead and jump into our new rule for today, another application of derivatives, aptly named as we're in the applications of derivatives section, and let's get to it. There are 6 limits. Yes, limits, those guys that are up here. Your goal is to determine the answer to each of these limits. Whenever you're ready, get it. Ready, set, go. You might have done really well with some of these and struggled with some of the others. So let's start with the ones you should have done well with. Those are the ones with dominance. And dominance only applies at infinity. So these two, we can use dominance on. The way dominance works is it says, is there really a difference in the parabola x squared minus 4 versus just x squared? And there is not. Same thing over here, which means we can reduce this. X squared over x cubed is 1 over x. 1 over something infinitely large is 0. Cool. We got 0. I'm proud of us. All right. What about C and F? That's a little bit harder because we can't just toss one of these out yet. We need to remember our order of dominance. And our order of dominance says logs are the least dominant. Those are much less than, right? Remember that double inequality? Much less than x to some power. Keep using b here, which are much less than b to the x power, exponentials, which in turn are much less than x to the x power. That I think can finish it off. It's a good combination of those two. All right, looking at that then, let's think about dominance one more time. Natural log is much less dominant than e to the x power. So at infinity, e to the x power is so big that the natural log might as well just be a constant. Doesn't even matter, blots it out. So substituting in infinity, 1 over infinity is again 0. This guy though, e to the x over the natural log of x, same sort of dominance, where e to the x is much more dominant than the natural log, but when I substitute infinity and it's on the top of the fraction, this becomes infinity. And I really try not to say equals infinity because we reserve equals for values, and infinity is not a value, it's a concept, right? It just means it tends towards something really, really large. So those aren't bad. Also not bad, but tricky, is this part D. This part D, reminding you, looks like that limit as h approaches 0 of f of x plus h minus f of x over h, which means this is finding f prime of x. Or if there is a value plugged in for x, as there is up here, that's fine. We might as well keep pi in here. It's not going to hurt. This is finding f prime of pi. So if I wanted to find f prime of pi, there are 3 steps. The first step is, what is f of x? Well, There is no f of x written at the end, but I'm pretty convinced based on this that f of x is sine of x. Then if we want to find f prime of pi, the first thing we need to find is f prime of x, that's cosine of x. And then the last part is f prime of pi, cosine of pi, which is -1. So the value of this limit is -1 because it's a definition of our derivative. You might have said, oh my gosh, we only covered that on like day 24. That was half a lifetime ago, literally half the number of lessons ago. You're right. I don't remember that, and that's okay. And the reason it's okay really has to do with B and E here. B and E, you probably don't know how to do. Now, some teachers that are either, you could argue, better than I or I don't know, more draconian than I, would require you to memorize the difference of cubes factoring pattern. I don't require that of my students because it's not needed. It's just something else to memorize, and although you could do this, you may remember, by the way, and I'll show you how this would go, you may remember x squared minus 4. I hope you remember this is the difference of squares, but you may remember the difference of cubes pattern looks something like this. Let's see if I remember it. Awkward. Looks something like this. Do you remember that this factors to that? I bet you didn't. And if you did remember that, then you could certainly cancel this and substitute in 2. But if you didn't, or even worse, I won't judge you too much out loud, if you factored x cubed minus 8 as x minus 2 times x minus 2 times x minus 2, A, you're wrong, and B, don't do that, and C, it's not right. So if you remembered how to factor it, super cool, canceled everything out, proud of you, very impressive, because we haven't talked about it at all this year, didn't do it in pre-calc either, just algebra 2, that was forever ago. However, what I assume most of you did is you probably plugged in 2 first. And you plugged in 2, you got 4 minus 4, we don't need the limit after we start to evaluate, 8 minus 8, and we got 0 over 0. So what I bet a lot of you did is you said 0 over 0 does not exist. And sadly, that is not the case with limits. 0 over 0 does not mean does not exist. This is indeterminate. It means we need to do more, right? It would be the same thing if you, over here, substituted in infinity, and you'd get infinity squared minus 4 over infinity cubed minus 8. Infinity squared is infinitely large. Infinity cubed is infinitely large. Different scales of infinity, but you get the idea. This is also indeterminate, right? The answer ended up being 0, not 1. And so we need to start to recognize these indeterminate forms here are not answers. And in fact, the AP exam is very much not a fan of this 0 equals 0 over 0. In fact, if you put this, you automatically lose a point and they yell at you. So same thing down here, you get 0 over 0, and if you put that again, they are real sad. So B and E are kind of interesting situations where if you memorize that pattern for difference of cubes, or you'll need the sum of cubes as well, you can get the answer. But with what I'm about to show you, you don't need to memorize that. And why memorize something extra when you have to memorize what follows as well? All right, there are 2 other problems down below, and it might have been a while since you've seen these. And remembering this order of dominance, you should be able to get through them. So go ahead and pause me again, give it a shot, unpause when you're ready. All right, we should be back now. Just a reminder, if you wanted to see what equals 0, this one does equal 0. More dominant, 1 over infinity is 0. This next one does not equal 0. We already did this one, right? More dominant, infinity over 1 is infinity. The last one, x to the 99th and e to the x, even though this has a huge power, that still falls under this guy, which is less dominant than this guy, which is an example, e to the x. So this is 1 over infinity, which is 0. All dominants, very cool. Last but not least, evaluate both limits below, while the 2 limits are, of course, as x approaches positive infinity and the limit as x approaches negative infinity. Positive infinity, not bad. I mean, technically you shouldn't replace this with infinity. I'm going to be a bad person for a second. But if we have something infinitely large times something else that's infinitely large, would it be wrong to say that that is infinitely large? And remember with a limit, if you're not sure if it's infinity or negative infinity, you really should just put does not exist, because it doesn't, there isn't an actual value it exists to, it is just infinity, or it is just does not exist. However, you can put infinity, but if you put a negative, you get the problem wrong. So does not exist is that safer answer. Versus over here, What I'm going to do first is probably split this up a little bit. I'm going to go ahead and substitute in my negatives first. So as x approaches positive infinity, it will be negative x times e to the negative x. And quickly rewriting with our wonderful algebraic skills, we get negative x over e to the positive x, right? Negative exponents. And then when we substitute in infinity, well, this is not very dominant at all. So this is the same limit as x approaches infinity of 1. I mean, negative 1 if you want that negative on there. You can leave the negative out front if it makes you happy. 1 over e to the x, which is negative 1 over infinity, which is just negative 0 or 0. All right, let's get to our new stuff, though. L'hospital, which is not correct, l'hôpital or l'hôpital. They're pronounced the same way. The new French spellings came around in, I don't know, like the 1800s, something like that, and they changed some of the notation and used new letters to make up for the old stuff. You'll actually find that l'hospital, which a lot of my students say, l'hôpital, is the more common spelling because people don't like writing that O with that cool little, caret above it there. So you can write either one. They'll know exactly what you mean. A lot of people just abbreviate L apostrophe H. Either way, always good to get a backstory here. So l'hôpital, alive from 1661 to 1704, so not super old, right? 43. This is right in the time when calculus was coming out, right? Calculus was popular in that early to mid 1600s, really big deal. L'Hôpital was a French nobleman, though. He was unfortunately born with bad eyesight, which really bummed him out because one of the big things to do for the French nobility in those days was to go serve, air quotes, serve in the military, where they really just sat back and they watched other people stab each other and then took credit for it. But they did actually have to have eyesight and make calls in battle. And because he had such bad eyesight, they actually drummed him out of the military. He went to sign up and they're like, no, goodbye. Well, he was like, well, what else am I going to do to earn myself a distinguished name? He's like, I'm not good at a lot of things, but I am good at math. Shocking, right? And although he was good at math, he's probably better than all of us, he wasn't the best at math. And in a time where communication is not super high, takes forever to get one place to another, you really had to be an amazing mathematician to be a famous one. However, he was clever. And he realized that he actually had money. So he was on like the French Mathematical Council. Yes, there were things like that. And so he discussed math and new math theorems and whatnot with all the other countries in Europe. But again, he had money. And so what he ended up doing is he reached out to up-and-coming mathematicians and said, hey, if you tell me your new theories a year ahead of time before publishing anything, and a year ahead of time wasn't that big of a deal because what are you going to do? Hold on to it for a year, tell someone, and no one's going to care? I mean, you tell one person and it takes forever to spread. A year ahead of time was not a big deal. So he said, if you tell me your discoveries a year ahead of time so I can work with them, become acquainted with them, maybe even publish them, though we didn't say that, then I will pay you a monthly stipend. And so his biggest clients ended up being the young, that was scary, the young Bernoulli brothers. And the Bernoulli brothers did many, many, many things, lots of physics, lots of math, and you can learn about them in other classes as well. But what L'Hôpital did, and yes, he was shady, he eventually published the first book with differential calculus, right? Differential meaning taking derivatives of calculus. And he published this in the late 1600s. So what ended up happening is it was a very well-regarded book. It was a good book. There was no debating that. But the problem was he pretty much took credit for everybody else's mathematical discoveries, and nothing in there was really himself. He did put it all together in a book, so I mean, power to him. And he did write one preface, a literally one-page preface that said, thanks to, and then listed a bunch of names. However, everyone just attributed it to him. And so in this book, one of these rules was stated, and he wasn't so egotistical to call it L'Hôpital's rule. He just stated a rule, and no one had seen it before, though, because it was attributed to the Bernoulli brothers, but he didn't say that either. And they said, wow, this L'Hôpital guy, this is L'Hôpital's rule. And in fact, what ended up happening is they went to court to try to sue him, right? The Bernoulli brothers and other people, and they're like, wow, you stole our ideas. And he said, haha, so long, and then he died. So there was really never any, any closure here. And the Bernoulli brothers didn't get made famous until after they died in the mid-1700s. So it's kind of a sad story there. But either way, we called it L'Hopital's rule back then, and that is the name that has stuck. So here we go. L'Hopital's rule. If, when you are evaluating a limit, you get an indeterminate form, such as what we've seen indeterminate forms before, 0 over 0, you might get infinity over infinity, you could get negative infinity over infinity, or you could get negative infinity over negative infinity, any combination of infinities like that. Those are indeterminate forms. Then, the limit of the derivatives is equal to the limit of the original function. And this is wild, because on the previous page, none of these, with the exception of D, had anything to do with derivatives. They were just straight limits. However, what the Bernoullis found, what L'Hopital stated, is that if you have some ratio, some fraction of a numerator and denominator, and you take the derivative of each one of these straight across, no quotient rule, nothing weird. If you just take the derivative and then you find the limit of the derivatives, you basically look at the ratio of the slopes together, that answer was equal to the original limit, which is fascinating. And there's a very cool proof and a good exploration, but we don't have enough time for that. Now, a bunch of important notes, and I think I'll cover everything here. First, do not use the quotient rule. You'll notice that this is not the quotient rule. Right? This is not a derivative. This is an application of derivatives to make a limit easier. Second, if when you take the derivative and then you try plugging in a, you get an answer that is still indeterminate, so you get 0 over 0, infinity over infinity, then just do L'Hopital's rule again. And so then you could also say through L'Hopital's rule, and I like the little L apostrophe H over the equal sign, so it's very clear as to what you're saying, that we get F double prime of X over G double prime of X. And guess what? If that's still indeterminate, then use it again. However, as soon as you don't get an indeterminate form, you cannot use L'Hopital's rule. I see a lot of people going through and they're like, ooh, the limit as X approaches, we'll say 3 of X over 6. Well, if you plug in 3, you get 1/2. You cannot use L'Hopital's rule here. You didn't get 0 over 0 or infinity over infinity, and that's a no-go. Even if you got something like 1 over 0, that's not indeterminate. That does not exist. You cannot use L'Hopital's rule. So it only applies, and this is the hardest thing for you to remember, for an indeterminate form. Now, this year, we only cover some basic indeterminate forms. There are many others, right? Is 0 times infinity infinity? Is it 0? Is infinity minus infinity 0? Is it some other infinity? 1 to infinity is 0 to the 0, infinity to the 0th. Your book actually covers with how to deal with all those other ones. So if you can, look it up. There's some cool stuff there, but the AP exam will never ask you to do any of these. Part E, definition of the derivative limit designers hate L'Hopital's rule. I heard that from a presenter one year, and he basically said, if you want your students to learn the definition of the derivative, don't teach them L'Hopital's rule, because L'Hopital's rule will cheat this question. We'll be able to find -1 without knowing this is the definition of the derivative, because we're sneaky sly. Now, could you have done this with the definition of the derivative? Of course, that's what we did earlier, right? And many of these limits you're able to do without L'Hopital's rule, but sometimes L'Hopital's rule just makes it easier. Last but not least, and I kept it last because it's so important, and we're going to write it underneath here. Man, when I talked about the AP exam being picky about things for the IVT, differentiability, continuity, we hadn't even gotten to L'Hopital's rule yet. You must show the separate individual limits of the numerator and denominator to justify using L'Hopital's rule. What does that mean? It means that if you show the limit as x approaches a of f of x over g of x, and you find that it's indeterminate and say equals 0 over 0, therefore we can use L'Hopital, they will crucify you, which is a little aggressive. They won't do that. But they will say, nope, that's not justification. Wrong. Because you're saying the limit equals something that 0 over 0 does not exist. I don't know. It's an error. And so you're saying that the value of the limit is an error, when in turn, the value of the limit is actually a number. So they hate when you do that. what do they actually want you to do? They actually, in this part you should write, they want you to show the limit as x approaches a of f of x equals, and then whatever it equals. And then they want you to show the limit as x approaches a of g of x and find what that equals. Completely separately. Even though it's together, you have to show it separately. Now, I'll show you a shortcut that I like to do in just a second. But you must do that. If you don't do that, you will have automatically lost yourself a point. L'Hopital's rule is usually between 2 and 3 points on a free response, usually 3. And the first point is this. You have to keep that in mind. So let's rock and roll. Every single one of these results in an indeterminate form. So every single one of these, you can use L'Hopital's rule. However, we are going to justify on every single one why we can use it. So our first one, the limit as x approaches infinity of x squared minus 4, and directly underneath the limit as x approaches infinity of x cubed minus 8. This becomes infinity. This becomes infinity. Therefore, L'Hopital's rule. And that's fine. You could literally write that and you would be just fine. Let's use L'Hopital's rule. And I'll switch colors to keep it clear. The limit as x approaches infinity of x squared minus 4 over x cubed minus 8 equals, through L'Hopital, I really like this notation, you don't have to show it, but I think it's really nice, becomes the limit as x approaches infinity. Just take the derivative of the numerator. X squared minus 4 just becomes 2x, minus 4 is 0, x cubed minus 8, 3x squared. Now, you have two options here. Option one is you can try plugging in infinity again, but you're going to get infinity over infinity. So you'd have to go through this process one more time and take L'Hopital's rule one more time. However, can't we simplify this, right? The limit as x approaches infinity of 2 over 3x. The x's, right? Reduce. And then if you substitute in infinity, 2 over infinity is 0. And that is, of course, what we got earlier. And you might start to realize, well, wait, I was able to do that way faster just by using dominance. Why would I use L'Hopital's rule? And that's a great answer. And the answer is, hopefully you wouldn't. Hopefully you would use dominance because it is faster. There are certain scenarios, though, like B, where you have to use L'Hopital's rule. Rude. So here we go. L'Hopital. First, we need to check or show that each of these derivatives is 0, and they are 0 in this case. X cubed minus 8 equals 0. Therefore, you can apply L'Hopital's rule. And you should say, as you get an indeterminate form, or as both limits are 0, or the limit of the numerator, limit of the denominator is 0, that's fine. However, you'd probably be able to get away with just this, and we're going to use L'Hopital. The limit as x approaches 2, take the derivative of each, x squared minus 4, that is 2x, x cubed minus 8, that is 3x squared, and then evaluate each at 2. 2 times 2 is 4, 4 times 3 is 12, that reduces to 1/3. Cool. Now, but wait, I did mention earlier that if you went through and you found L'Hopital's rule, that you wanted to avoid the pitfall of continuing to take L'Hopital's rule. You'd be like, oh, I don't like this. Let's take L'Hopital's rule again, right? So 2x divided by 3x squared. And you're like, I'm going to do L'Hopital's rule again because I'm an overachiever and I want to see how far it'll go. Well, the derivative of 2x is 2, 3x is 6x. But what happens if you evaluate it 2 now? We get 2/12, which is 1/6, which is the wrong answer. So as soon as you use L'Hopital's rule on a function that is not indeterminate, you get that wrong answer. So be very careful there. Okay, let's look at another. Part C. We said this one was 0 before, so it's probably a good example. Give myself a little more room here. Limit as x approaches infinity of natural log of x is infinity. And again, I avoid using that 0 there. I'm just not a fan of saying, or that equals, or I'm not a fan of saying something equals infinity. Those both tend to or go to infinity. So that's fine there. L'Hopital's rule, so the limit as x approaches infinity, 1 over x for natural log, and e to the x stays the same. Well, this one gets kind of weird, because if you plug in infinity, you get 0. And if you plug in infinity, you get infinity. 0 divided by infinity, that's one of those indeterminate forms that and I guess, sorry, I should have used L'Hopital here. That's one of those indeterminate forms that we don't cover here, right? But we could rewrite this slightly without using L'Hopitals. We can say that this is e to the x over 1 multiplied by the reciprocal, 1 over x times 1 over e to the x, and continuing to clean up, 1 over x e to the x. And now it's not bad at all, because if you substitute an infinity in the denominator, it's infinity. I mean, infinity times infinity is infinitely large, so you end up getting 1 over infinity, which is 0. And so you can see that same 0 that we found before. Was dominance faster? Certainly it was. All right, the last one that I wanted to run through is part D. Part D is an interesting guy, because this is a definition of the derivative. And as a reminder, what you really should try to do first is substitute in 0. And so I'll show that right now. The limit as h approaches 0 of sine of pi plus h is going to be the sine of pi plus 0, which is the sine of pi, which is 0. And then the limit as h approaches 0 of h, substitute in 0, we get 0. 0 over 0, indeterminate, L'Hopital time. Now, if I do L'Hopital using the space up above, we're taking the derivative with respect to h. So the limit as h approaches 0, the denominator is easy. The derivative of h is 1, not dh dt or anything weird. It's just with respect to h. The derivative of sine of pi plus h becomes cosine of pi plus h times the derivative of the inside, which is just 1. Then we need to substitute in 0, so it just becomes cosine of pi plus 0, which is cosine of pi, which is negative 1. And looky here, we have done a nice job of skirting around the idea of the definition of the derivative because we know L'Hopital's rule. I am proud of everyone. All right. I think all the rest are pretty straightforward, E and F, nothing too bad. You should try them with L'Hopital, but really we should move on to our last 2 pages here. These last 2 pages are all about some multiple choice practice, and they are definitely worth going through. I'm going to check the time really quickly, 36 minutes. I think I probably have enough time to talk you through all these. I like that better than just giving you worked out solutions, but realistically, you should try to work all these out on your own and then check the answers after, because man, it is boring to just listen to me talk. So give yourself an attempt on each of these. You can do one, watch one, or do them all and then watch them all. Ready, set, go. All right, and we're back. Looking at this, let's go ahead and give this a shot. So maybe we use L'Hopital's rule on all these, maybe we don't. And the way that I always get around it is I show the 2 separate derivatives over here, and a lot of times they won't write the equal sign, but I show the derivative of the numerator, 4x squared, that's 0, and then I show the limit of the denominator right underneath. No fraction line, just right underneath. And the reason I do that is, I'll show you in just a second, this becomes, by the way, 1, 0, 1, 1 minus 1 is 0. Well, let's say that the denominator had become 4. Well, then it's not L'Hopital. The answer is 0. All I would do here is just draw a fraction line, scratch out my equal signs, and draw a fraction line, and then we just get 0. And bam, you're done. Super easy. So I stack one on top of the other instead of going side to side, just in case it's not indeterminate, and then you don't feel like you've wasted your time. So we end up getting 0 over here, 0 over 0 is L'Hopital. So through L'Hopital's rule, we end up getting the limit as x approaches 0, derivative of the top, 8x, derivative of the denominator can be a little more challenging. E to the 4x is itself, times the derivative of the power, which is 4, minus 4. Let's substitute in 0 again, and I'll do the same thing as before. So the limit, and leave a little space so I can fit both of them. The limit as x approaches 0 of 8x is 0. And the limit as x approaches 0 of 4e to the 4x minus 4. This becomes 1. 4 times 1 is 4. 4 minus 4 is 0. We're going to use L'Hopital's rule again. How exciting! Here comes another L'Hopital rule. The limit as x approaches 0. Derivative of 8x is 8. Well, that's not turned into 0 again. And then the denominator, e to the 4x times another 4 is going to give you 16 e to the 4x, right? Because its extra 4 is going to hit that 4 one more time. And then that 4 becomes 0, so nothing bad. Now let's substitute in 0, 8 over 16, which is 1/2. Now, of course, this is a multiple choice question, and if I were doing this multiple choice on an actual test, there's no way I'd show all this work, right? I'd just scratch out a couple derivatives, plug in 0, and we're good. But I think it's important, if time is not of the essence, to show all those extra steps so it's in your brain for the free response. All right, next one. Here we go. Substituting in infinity, we do need to show this separately. The limit as x approaches infinity is the natural log of e to the 3x plus x, which if you substitute in infinity, this becomes infinity. Natural log of something infinitely large tends to infinity. Same thing down below. The limit as x approaches infinity of x also tends to infinity. Indeterminate form, l'hôpital. Here we go. My French accent, by the way, is terrible. I went to France 2 summers ago now, thanks quarantine, and it was awesome, but man, my French is not good. Okay, so derivative of the numerator, and we need our limit first, don't we? As x approaches infinity, this one's tricky. The numerator here, denominator I guess is 1, the numerator becomes 1 over what's inside, e to the 3x plus x. But that is just the derivative of natural log. It's 1 over what's inside. So we need to remember to multiply by the entire derivative of what was inside. And the derivative of e to the 3x is 3e to the 3x plus 1. And it must be grouped in parentheses unless you already wrote it on top of the fraction. Don't forget that anything over 1 is itself. So this is the limit as x approaches infinity of 3e to the 3x plus 1 over e to the 3x plus x. Well, looking here, I think we're again going to find infinity over infinity. And I'm running out of room, so I'm going to use my infinite paper off to the side. I apologize. We'll show this one more time. It's good practice. 3e to the 3x plus 1 goes to infinity. And also, e to the 3x plus x goes to infinity. So we should probably use L'Hopital's rule one more time. How exciting! The limit as x approaches infinity, the numerator becomes 9e to the 3x, and I think you'll be able to see why with that extra 3 coming down, and the denominator is 3e to the 3x plus 1. Oh my gosh, do we have to keep going? I would actually argue no, we don't. And the reason why is I'm just going to use dominance at this point. Why would I go further? In fact, I could have used dominance over here and still gotten the same answer, but we might as well. Dominance-wise is a great way to avoid having to use all that setup for L'Hopital, right? Dominance, we're just going to say that that limit will have the same value as this limit, plus 1 doesn't matter at infinity. These reduce, we get 9 over 3, which is 3. And I mentioned you could have done it earlier too. Looking over here, not dominant, cancel, 3. Woohoo! Go us. Could we have done it at the beginning? That would have been a little bit harder. Doable maybe, but harder. Doable because this is not dominant. These cancel. Then the x's cancel, and you're left with 3. But that is a bit of a stretch of our dominance. All right, free response practice. Let's rock and roll. Continuous function is below f. They give us a point. Find a limit. Okay, well, let's go ahead and actually take a limit here. Again, it looks like it might be L'Hopital, so let's try L'Hopital. But before we do L'Hopital, let's do the setup. The limit as x approaches 1, kind of keeping in line with this fraction, of 10 to the x minus 3 f prime of x. And then also in the denominator, the limit as x approaches 1, f of x minus the arctan of x. Now, they told us that f is continuous, which is very nice. I always like to cover my bases, though, because what we're going to do is I always like to make sure that if it says it's continuous, but they don't actually give us an equation, I think it's really important to state something like this. As f is continuous, and we talked about this for the squeeze theorem too, then f of a is equal to the limit as x approaches a of f of x. And that's important because a limit is not always equal to the value at a point, right? So this limit isn't necessarily equal to f of 1, but it is if f is continuous. I think that's an important kind of blanket statement to put if they don't give you an equation, if they give you a table, if they give you a graph, something like that. And sometimes this isn't important, sometimes it is, and it's better to err on the side of caution. So let's work out each of these. The one in blue first, let's see, I'm going to try to line up my equal signs in case I need to erase, is going to be 10 to the first minus 3 times f prime of 1. And the one in gold is going to be f of 1 minus the inverse tangent of 1. Oof, inverse tangent, who invited you? Continuing out, this becomes 10 minus 3 times f prime of 1. F prime of 1 is right here. That's f of 1. F of 1 is 1. But f prime of 1 measures the slope of this line, which hopefully we can count, up to over 1. F prime of 1 is 2. And down here, f of 1, well, we just saw f of 1 is 1, minus inverse tangent of 1. OMG, that sounds awful. Well, inverse tangent of 1 is really saying tangent of what equals 1. Right? If you do inverse tangent, it becomes inverse tangent of 1. Well, I like to think of it as sine divided by cosine equals 1. So what they're saying is sine and cosine have to be the same value. And when you divide the same value by itself, you get 1. Where are sine and cosine the same? At pi over 4. So this becomes 1 minus pi over 4. I don't think any of these are 0. I don't think we're going to be using L'Hopital's rule. And you're like, oh no, do I have to erase all this? No, you don't. It's very easy. It equals, we are allowed to distribute the limit to the numerator and denominator, and then we just keep our fractions. I would probably scratch these out just to show one equal sign, and then great. You're on track. We didn't have to erase anything, nothing too bad. And you're like, but how does this simplify? Well, honestly, once you get down to numbers, I'd just stop here. However, we can go a little further. 10 minus 6 is 4. 1 minus pi over 4. You could clean up. You could put them as both 4 over 4 and multiply, but I really don't want to. So that seems just fine to me. All right, second one. Let f be the function, blah, blah, blah. Let g be differentiable such that g of 2 equals 0. And we also have the graph of g prime. Find the value or state that it does not exist. Justify your answer. We'll use some space over here. So same thing as before. We're going to find the limit as x approaches pi over 2 of f of x. And we're going to find the limit as x approaches pi over 2 of g of x. All right, the limit as x approaches pi over 2 of f of x is easy because we have a function, e to the pi over 2 times cosine of pi over 2. I don't know what e to the pi over 2 is, but cosine of pi over 2 is 0. Anything times 0 is 0. G of x. You'd probably be tempted to say, oh, that's g of pi over 2. And g of pi over 2, they told us, is 0. However, remembering this problem when we graded it a few years back, you actually lost a point for doing that. And again, that comes back to what I mentioned up above. Their question would be, wait, how do you know that this is the same as g of pi over 2? Are you making the assumption, because we don't have the graph of g, are you making the assumption that at pi over 2, the point and the limit are at the same spot? What if they're in different spots? What if this is up here, and so the limit is actually bigger than 0? I guess this should be probably down at 0, huh? How do you know that? Well, hopefully looking back at the problem, you'd say, well, g is a differentiable function. If g is differentiable, then what do we know about g? Right? As g is differentiable, then g is continuous. Therefore, g of a is equal to the limit as x approaches a of g of x, right? This is our definition of continuity right here. So important. So that way you can actually state this relationship. Cool. We've shown that. Let's use L'Hopital's rule. Equals L'Hopital, the limit as x approaches pi over 2 of f prime of x divided by g prime of x. And let's try again. Okay, having done this before, you don't need to do another derivative, so let's do it right here. We're going to do the limit as x approaches pi over 2 of f prime of x. And we're going to do the limit as x approaches pi over 2 of g prime of x. And this is going to equal, and we'll stay in red, f prime of pi over 2. This one's going to equal g prime of pi over 2. And let's finish this off. So g prime of pi over 2, Well, we have a graph, and this is tricky. I see a lot of students make mistakes here. You say, oh, sharp point, the derivative doesn't exist. And you're right. The derivative of this graph doesn't exist. This is the graph of g prime. So g double prime of pi over 2 certainly does not exist. But g prime of pi over 2 absolutely exists. There is a point here. There's a closed, there's no open circle. There is a point. G prime of pi over 2 is 2. All right, well, if we look at g prime of, or if we look at f prime of pi over 2, we have to do a derivative, don't we? This problem's super involved. So let's find f prime of x. It is derivative of the first, that stays the same. Keep cosine the same, product rule, right? First one the same, derivative of cosine, negative sign. And then we need to find f prime of pi over 2 here. Might as well show it up above where I have some space. E to the pi over 2 times cosine of pi over 2. We already saw that whole thing became 0. Plus e to the pi over 2 times negative sine of pi over 2. This is 1, but there's a negative, so this becomes negative e to the pi over 2. Negative e to the pi over 2. We did not get 0 over 0. We did not get an indeterminate form. So let's throw in those equal signs and call it good. Equals, boop, boop. Scratch out these. And there we go, our final answer. Definitely a tricky problem. Lots of different things going on between derivative of an equation, looking at the graph of a derivative. Dang, it's involved. This was out here 2 years ago, though, on a free response. It was worth a lot of points, but it is certainly tough. Okay, last problem for today. A, B, C. I am excited to see what we come up with. I'd actually like you guys to try this one, and then we'll come back together. Okay, we're back. You have actually seen this problem before, but it's been a while, and I think you've only seen it once, maybe twice. I've shown you this with the squeeze theorem before, but I cut the squeeze theorem out of this one. So let's go ahead and see what we can do. First one, h prime of 2. Well, since we know that this equation up here, and you might like it better written as 2/3 x minus 2 plus 4, so you can see that hk form. It's tangent to both the graphs of g and h, which means we could treat this tangent line, and I'll maybe do it up above where I have space, as y equals g prime of 2 times x minus 2 plus g of 2. Or you could think of it as h prime of 2 times x minus 2 plus h of 2. And so we know a couple things. We know, of course, that g of 2, h of 2, and 4 are all equal. They told us that, yeah? But we also know that g prime of 2, h prime of 2, and 2/3 are equal. So when they say find h prime of 2, and this was literally a free response question like 2 or 3 years ago, it's very easy. H prime of 2 equals 2/3. That's it. There's no justification, no work. It's just, do you understand what tangent lines are? Cool. Part B. Let a be that function, find an expression for a prime, and then a prime of 2. So first problem was worth 1 point. This problem is actually worth 3 points, which I thought was a lot for just doing a product rule and then plugging something in, but 3 points. It was 2 points for the product rule. So we have a prime of x, derivative of the first is 6x, keep the second the same, keep the first the same, and then the derivative of the second. Then we had to find our value at 2. So 6 times 2 is 12, h of 2, whoop, and then 2 squared is 4, 4 times 3 is 12, very nice, and h prime of 2. H of 2 we defined up above as 4, and h prime is 2/3. So a prime of 2 is 12, and then h of 2 we said was 4, and then 12, and h prime of 2 is 2/3, so cleaning this up, 48, let's see, let's reduce this one, 4 times 2 is 8, looks like 56. Nice. Part C, the fun one. Here is a crazy function h of x. Oh, but wait, we know h of x. Actually, we don't know h of x. We know 2 things about h of x, and these are very important. We know that h of 2, let's see, h of 2 we learned was 4, and we also know that h prime of 2 is 2/3. That becomes important. But here we go. It's known that the limit as x approaches 2 of h of x can be evaluated using L'Hopital's rule. Use the limit as x approaches 2 of h of x to find f of 2 and f prime of 2. Show the work that leads to your answers. This question to me was hands down the trickiest. C and D were the trickiest problems on the entire exam this year. This is maybe 2017, something like that. Why were they so tricky? Well, first, there's like a million functions going on. We have h, we have f prime, we have h prime. Oh my gosh, we have another h of x. Well, one thing to remember, and that is that h is differentiable, which means that h is also continuous. And if h is continuous, then h of 2 is equal to the limit as x approaches 2 of h of x. Continuity. Woohoo! So let's go through this. It's known that the limit as x approaches 2 of h of x can be evaluated using L'Hopital's rule. So let's try that first. Let's just try taking the limit as x approaches 2 of each side of this equation. We're going to need kind of two columns here, if I remember correctly. So the limit as x approaches 2 of h of x has to be equal to the limit as x approaches 2 of x squared minus 4 times 1 minus f of x cubed. Well, with any limit, we should probably just try evaluating at 2, shouldn't we? So on the left side, evaluating at 2 gives me h of 2. On the right side, I see a fraction, so I'm hesitant. I'm going to probably go through and do it as a split here. X squared minus 4, and the limit as x approaches 2 of 1 minus f of x cubed. Well, this guy over here becomes 0, clearly. And wait, didn't they say we could evaluate this using L'Hopital's rule? So if I know the top becomes 0, and we can use L'Hopital's rule, doesn't the denominator have to equal 0 as well? I think it does. And in fact, I'm going to get rid of this really quickly. To use L'Hopital's rule, this has to happen because the top becomes 0. So because f, right, and I think they tell us up here, f is also differentiable, which means f is continuous, I think we are allowed to substitute 2 in here. And so just working with this guy, let's take a look. Substituting in 2, I get 1 minus f of 2 cubed equals 0. I bet I can evaluate f of 2 now. 1 equals add f of 2 cubed to the other side, cube root both sides, cube root of 1 is 1. We just found f of 2. Ho-ho! Look how good we are there. They asked us to find f of 2 and f prime. We found f of 2 without even using L'Hopital's rule. We just knew that in order to use L'Hopital's rule, the denominator had to become 0. The only way it can do that is if this is 1. 1 minus 1 is 0. Nifty. Okay, well, what next? So we haven't found f prime. Well, I think in order to introduce f prime, we probably need to actually take L'Hopital's rule. So let's maybe do it like this. We'll do the same thing again. We'll do the setup. We'll switch colors. We'll say the limit as x approaches 2. Oof, tough time. As x approaches 2 of h of x is equal to the limit as x approaches 2 of x squared minus 4 over 1 minus f of x cubed. Well, this left side we know is h of 2. The right side, though, we know can be evaluated using L'Hopital's rule. So let's do L'Hopital's rule. We don't need to do the 0, 0 thing. They already told us we could do that. 2x, 0 minus, derivative of this guy. Gnarly. 3 comes down, f of x reduced by 1. And then what does everyone forget? The chain rule. Derivative of the inside is f prime of x. Nice. Let's continue. We know h of 2. h of 2 is 4. So we can replace h of 2 with 4. And on the right side, let's just start evaluating it 2. So we get 2 times 2 over negative 3 times f of 2 squared times f prime of 2. Can we clean this up at all? I think so. Maybe 4 over 1. We get 4 over here. This is negative 3. F of 2. Oh, we know f of 2 as well. How exciting. F of 2 is 1. So it becomes 1 squared times f prime of 2. Cleaning this up more, 4 over 1 equals 4 over negative 3 times 1 squared, just negative 3. And then to isolate f prime of 2, I'm going to use my favorite trick. I'm going to flip both fractions to bring f prime of 2 to the top. And something like this. And then we just isolate. Multiply both sides by 4. Boo! That gives me 1 equals negative 3 times f prime of 2 divide by -3. -1/3 is f prime of 2. What a wild problem. It was, I thought, extremely tricky. Never seen one like this before, but it's a great application of L'Hopital's rule. If you understand this problem, you understand everything we have done today. So thank you for being so awesome. I'm excited to see you. We only have 3 new learning days left for this semester. All of it is on a topic known as particle motion. It connects calculus to physics, and that is all. So good luck, and I'm excited to have you back next class.